How do you use Ray, DeepSpeed, or PyTorch Lightning for scaling AI training? Scaling training with these tools comes down to moving from one GPU to many without losing control or rewriting your entire pipeline. Distributed training becomes simpler because orchestration, device placement, and communication patterns are handled behind the scenes. And faster development comes from letting each GPU work like a focused cook in a well-organized kitchen. If even one waits 5 or 10 milliseconds for instructions, throughput drops. Lightning cleans up your training loop. DeepSpeed stretches memory so 60 or 80 gigabyte models can fit. And Ray routes tasks across machines like a station manager directing trains. A strong interview comparison is Lightning simplifies code, DeepSpeed expands memory capacity, and Ray handles cluster coordination. Interviewers may ask where this approach struggles, and you can confidently say it breaks down when network fabric is too slow to synchronize gradients efficiently. A common follow-up is why Lightning alone isn't enough. And the short reply is that Lightning shapes training structure while Ray manages multi-node scheduling. It's normal if scaling feels abstract at first. The picture sharpens quickly with practice. You're already building real intuition about how distributed systems behave. 3 powerful scaling frameworks. PyTorch Lightning removes boilerplate and reduces overhead, acting like an assistant who handles repetitive tasks. Built-in multi-GPU support ensures tensors land on the right devices and stay synchronized. On an 8 GPU system, this can save 10 to 20% of engineering effort. DeepSpeed uses zero memory optimization to spread parameters and optimizer states across GPUs, like distributing heavy luggage so no traveler is overloaded. A model needing 80 gigabytes might run at 40. Its memory efficiency often yields 30 to 50% better throughput. Ray scales work across clusters, coordinating dozens of workers and letting you run hyperparameter sweeps like testing 30 recipes at once. Interviewers may ask when DeepSpeed adds overhead, and the answer is small models, where zero partitioning does more work than necessary. Another follow-up is when Ray becomes essential, and you can say when elasticity, scheduling, or multi-node experimentation is required. A simple comparison that lands well is Lightning simplifies training logic. DeepSpeed handles extreme model sizes, and Ray orchestrates everything at scale. You're learning to choose tools based on real constraints, which is a powerful skill. You're doing great. Distributed training pipeline. A distributed pipeline flows through data loading, training, optimization, and checkpointing. Data loading is often the first bottleneck. GPUs may process a batch in 30 milliseconds, but the loader may need 40, leaving the GPUs idle, like chefs waiting for ingredients. Model training distributes batches across GPUs like a relay team, keeping a steady pace. Gradient synchronization in the optimization step can consume 30 to 60% of total step time on large clusters, much like a team regrouping before running the next lap. Checkpointing periodically writes snapshots, often 4 gigabytes each, so training can resume safely after failures. A strong interview insight is that compute is fast, but data movement and communication dominate performance. When asked where pipelines fail, you can point to slow pre-processing, weak storage bandwidth, or network links that lag behind GPU speed. A typical follow-up is how to detect these issues, and you can say by comparing data loader time to forward-backward time. If the loader is slower, the GPUs are starving. Don't worry if this feels dense. Distributed pipelines make more sense the more you visualize them. You're picking this up beautifully. Interview follow-ups. Choosing DeepSpeed over Lightning usually hinges on memory limits. Once a model pushes past 80 gigabytes, even in NIC's precision, zero becomes essential. Zero works by splitting parameters, gradients, and optimizer states, so no GPU carries the full load, like dividing warehouse inventory so no shelf collapses. Data parallelism copies the model across devices, while model parallelism slices layers across GPUs, the way different workers assemble sections of one machine. Fault tolerance depends on checkpointing and elastic training, so failures don't end the job. Monitoring throughput, idle time, and synchronization cost reveals where imbalance hides. 20 or 30% idle time signals communication delays. A helpful comparison in interviews is data parallelism scales wide, model parallelism scales deep, and zero eases memory pressure for both. Interviewers may ask where zero struggles, and the honest answer is tiny models where the overhead outweighs the benefits. Another likely follow-up is how to verify system health, and you can say by checking step latency and gradient sync time. You're learning to think with the nuance of someone ready for real engineering interviews. Real-world scaling workflow. A real production workflow begins by preparing the environment, installing frameworks, confirming GPU visibility, and ensuring fast links like NVLink or 100 gig networking, 10 gig networks often cut scaling efficiency below 50%. Strategy comes next. Choosing data or model parallelism, batch sizes, and precision modes. Doubling batch size can shave several milliseconds off sync cost. Launching training means distributing work across workers and watching metrics such as GPU utilization. Good runs stay above 90%. Optimization and deployment involve profiling bottlenecks, adjusting hyperparameters, and exporting the model. A proven pattern is to start with Lightning, bring in DeepSpeed for memory-heavy models, and use Ray when orchestration or large-scale search becomes necessary. So, a clear interview comparison is Lightning simplifies, DeepSpeed expands, and Ray coordinates. When asked where this workflow breaks, you can say when storage throughput or pre-processing can't keep up. A typical follow-up is how to detect it, and you'd answer by measuring data loader time versus compute time. You're developing the mindset that powers real distributed training systems, and you're doing excellent work. If this boosted your AI ML prep, smash that like. Comment your next interview question. I might feature it. Hit subscribe and turn on the bell so you never miss a breakdown. And share this with a friend who's prepping too. Let's get you both hired.